So this is the diagram to show where is the streamline and where is the potential line, because now we have two lines here. So we have a streamline and we have potential velocity lines. The first thing that you need to know is streamline is the actual streamline or the actual volume flow rate that occur in flow. So it can be proved in experimental work. For example, we could use a smoke generator in wind tunnel and we could see the streamline. And potential line is the imaginary line that we need to create perpendicular to the streamline. So this is the key point, the main idea that you need to understand. Potential line or velocity potential is an imaginary line that created in our diagram. It cannot be proved in experimental work. And the location of the velocity potential, it must perpendicular to the streamline. So mean, for example, if we have this kind of streamlines like this, so the velocity potential line must be perpendicular to the streamline, and we need to draw it like this. So again, if we have a pipe here, so for sure the streamline or the flow rate that actually exists in the pipe is from the top here for flow to the bottom like this. So this is the line here must be the streamline, and we will learn how to get its stream function later on. And the phi here, the velocity potential, must be perpendicular to the streamline. So we need to draw a vertical line like this for this section, and then a little bit incline like this to make sure that at point here the cross section between velocity potential line and the stream line here must be in perpendicular condition. So it's inclined a little bit and it's become horizontal line here to remain the perpendicular condition like this. So this is the same thing if we have a velocity like this, and for sure the straight line is the stream function here, and then the vertical line will become the potential function or the velocity potential. So, and then we will learn about this later on. For example, we have situation where the molecule rotates in circular motion like this. So because the psi here will show the real flow rate, means that the circular path here will become the stream function or streamline. So we have a streamline 1 here, streamline 2 here, streamline 3, and streamline 4, and so on and so forth. So this streamline may be same in the value or might be different. So it's depend on our calculation. Later on we will see about the value of the streamline here. So in this situation, if our real condition, the molecule of fluid is moving in circular motion, so this circular line, the true line here is the stream function, is the streamline. Then the phi, the velocity potential line, must be perpendicular, so it will become like this. And again, every velocity potential line here will have their own value. Same with the stream line here, every streamline will have their own value. So again, if we have a real situation where fluid move from one point here to a direction of radial like this, move outward and parallel with the radius direction like this. So means that the flow from the origin here parallel with the radius here will become the psi, or the stream function, the streamline, because streamline must reflect the real flow of certain fluid. So then the circular line, the dotted line here, will reflect the phi, which is the velocity potential, and imaginary line to fulfill the drawing of this diagram. And this is the very important part. So we call it the Cauchy-Riemann equations. The Cauchy-Riemann equations named after Augustin Cauchy and Bernard Riemann. So it is actually the compilation of all equations that we get from the relationship between u and psi and u and phi, and also v and psi and v and phi. So it can be concluded as this table. For Cartesian coordinates, we could conclude that u is equal to d psi over dy, and it also equal to d phi over dx. For velocity component v, it is equal to negative d psi over dx equal to d phi over dy. For polar coordinate, it can be written as ur equal d psi over r d theta equal to d phi over dr. And u theta for polar coordinate is equal to negative d psi over dr, and it is also equal to d phi over r d theta. So I hope you could remember these, all of these equations that we call it as a Cauchy-Riemann equations. Or if you cannot remember this, please make sure that you could draw the diagram of Cartesian coordinate and polar coordinates, and you derive your own relationship between u and v, psi and phi, because we already learned about that previously, and we conclude all of the velocity and we call it as a Cauchy-Riemann equation. So this is a very, very important equation that you need to remember, because almost all the solution in this chapter is actually based on the idea of Cauchy-Riemann equation.